Audio Jungle. Audio Jungle.
Okay, so this is stresses in beam. Stresses in beams. Okay. Again, this is very important, and here we have to discuss bending moment, bending stress. Okay, all those things. For the different section, we have to also calculate that section modulus that we have to do. Anyway, so first we'll take one simple example. Suppose this is the beam. Okay, beam is nothing but horizontal structural member. If somebody asks you what is the beam, then you have to say it's a horizontal structural member. For this beam, we are having obviously one will be upper surface, another will be lower surface, and this axis we can take. Okay, this is the one axis. Okay, and obviously you also can say it's a layer, because this is the upper layer. If say this is upper layer, okay, this is the bottom layer, so this layer will be the middle layer. Okay, and this layer also we have to give the terminology that is called neutral layer, or if it is axis, then we can say it's a neutral axis. Why we are calling it neutral axis, that also we have to see. Okay, there is a reason why we are calling neutral axis. Anyway, so I can tell this is nothing but neutral layer for this beam. This is the upper layer, this is the bottom layer, and obviously in between upper and bottom layer, or lower level layer you can say, or bottom layer, top layer, bottom layer you can say, upper or lower also you can say, it's your choice. So top layer, so it's a bottom layer or upper and lower layer, anything you can say. So in between top and bottom layer, multiple layers are there. Okay, so which one is the middle layer? It's a in between top and bottom, in between, which one is the exactly middle layer, that also called a neutral layer. Why it is called neutral, we have to discuss. Now for this particular beam, this is a beam now. Okay, this is the beam. It's a, what is the beam? It's a horizontal structural member. Okay, just like a column is nothing but vertical structural member, so beam is nothing but horizontal structural member, right? Now for this particular beam, we have to check, once we'll apply the load, or once we'll apply the moment, so what will be the effect on the layer, top surface, on bottom surface, bottom layer, on neutral layer, what will be the effect of it, that we have to discuss here actually. All right, it's very simple. Now, as I told you, two types of moment already I had explained. It was sagging moment and hogging moment. Sagging moment and hogging moment. So that two moments we have to apply one by one, and we'll see the effect on this beam. I mean, on top layer and bottom layer and neutral layer, what is the basically variation, that we have to check. All right, that is our job now. So I can make two separate diagram. Okay, for this particular beam, this is the beam horizontal structural member, already I have shown you just now, and here also we have this horizontal structural member beam, right? This side will apply the sagging moment. So sagging moment, if you apply, so I can show you this. I just want to extend this something like this. First we have to understand the physical appearance after applying the moment, then we'll go for the mathematical model. Okay, for this particular beam, this is the axis, which is nothing but neutral axis, you can say, or neutral layer also you can say. Why it is called neutral layer, I will tell you. Okay, now for two different cases, now we are going to apply the first one, that is called sagging moment. If you apply sagging moment, so sagging moment means it will try to deflect beam in this way. That already I have discussed. This is called sagging moment. So for this beam, if this type of moment will work, something like this and something like this, then what will happen? If this type of moment will work, this is called sagging moment. What it is called? Sagging moment. Okay. And for this beam, we have to apply moment something like this and something like this. Okay. So if you apply moment something like this, then what will happen? That also we have to check. This type of moment called hogging moment. What it is called? Hogging moment. Okay. Now see, if this type of moment you first apply, which is sagging moment, then this beam will deflect in this way. Check nicely and you will understand. This beam will deflect somewhat. Upper layer will deflect somewhat like this. This will be the deflection of the beam, something like this. Yes or no? Obviously, this shape will be somewhat, because it is deflecting, so that actual shape of the beam will be like this. See, actual shape of the beam will be like this, right? So I can first part, this part I can remove. So your beam will appear something like this. See, your beam will appear something like this, because you are applying moment in this way. So this beam will deflect in this way. Obviously, this axis, which is nothing but, I told you already, this this axis you have to show something like this one, which is nothing but NA, that is neutral axis, NA. Okay, this is the surface AB, this is AB, and this is what? CD. Okay, this is AB, and so this is nothing but AB and CD. Now if you see, CD length is what? Extended, so you can say now CD dash, C dash, D dash. AB now distance, if you length you check, it is shortened, means decreases, so A dash, B dash, because actually it is not same. But neutral axis it is same. Why it is same, I will tell you. That I told you, this is the one surprise things, and we'll discuss later. This is very special actually. So first you see the physical appearance. Suppose there is the beam and you are applying moment in this way, moment M you are applying here. So what will happen? What will be the physical appearance of the beam, that you have to see first. The second, that is nothing but hogging moment, that also have to draw. Hogging moment, once you show, then this beam will be, you are applying in this way, so beam will be, see, this will be the beam. Now if you are applying moment, it's simple. You can take your book or any horizontal member, you apply, just hold the corner, you take your book, thin book, and just hold the, uh, that any two sides, and you just apply moment. Two types of moment I have shown you, sagging and hogging moment. If you see, if you apply, then you will automatically get this type of shape, so you can recognize that. Okay, here also this is nothing but PQ, this is RS, this is NA, neutral axis. So obviously here also we'll have a neutral axis, something like this. Okay, neutral axis. This is P, Q, and this is R, S. If you see PQ length, any length will be there, but now once hogging moment applied, this Q distance is length is what increased, so it becomes P dash Q dash. RS length is what shorten, it decreases, hence it becomes R dash S dash. This is the physical appearance. Once you apply the moment, or you can say load for the beam, then this type of curvature you will get. It's a very simple. You can practice at your home itself. Take it. I told you, take thin books and just hold two different sides. You just hold by your hand and you just fold one in upper direction, another in downside direction. So you will get this type of structure, right? Now coming to the points, which is nothing but the vertical. This is the vertical axis, obviously somewhere, and here also we'll have a vertical axis, right? I can show you like two different layer we have, like upper side layer. So this upper side layer we can take one section, and downside layer we can take one section. Similarly here also, and here also, right? Now coming to the check, because see this point you just check here, the actual length was AB length, but now it becomes A dash B dash. Now you see that length is what decreased, yes or no? If I say this length is nothing but L length, both beams, if this length is become nothing but L length, if you see this A dash B dash, now length is what decreased both side, na? Both side, this length here and this length is what removed, basically. See this side, both side, okay? Similarly here also, this and this, right? My point is A dash B dash is what length decreased now. Actually it was AB length, but now because of the sagging moment, A dash B dash decrease. When length will be decreasing? When there is the compressive load. So easily you can say A dash B dash is what under compression, because if it is under compression, or compressive load is at what acting, then only length will be decreasing. So easily you can say it's under compression. What you have to say? It's under compression. So this upper surface or top surface will be in under compression mode, and downside at the same time, if you check the downside, length C dash D dash is what increasing. So you can say well length will be increasing when there is the tensile load. So this bottom side layer will be under tension. Same concept you apply here. See here, the upper side length P dash Q dash, which is more than PQ length. Okay, so P dash Q dash length is what increasing. It means it is under tensile, or tensile load is what acting. So under tensile, or you can say under tension. You can say better word, under tension. This surface or this layer is what under tension. Because of the tension load only, this length is what increase. Hence it is under tension. All right. What about this? Check this R dash S dash, again length is what decreases. So once length is what now decreases, then your surface, which is the bottom surface, will be under compression. So this is the physical appearance. Before starting the derivation, we should aware with this. Okay, right. Now if you check two small elements I have taken, upper surface it is under compression. It means this surface will be experiencing compressive load. So compressive load means this is the compressive load. See, this is compressive. Bottom surface, that will be experiencing tensile load. Hence we'll have to show on this element, we have to show tensile load. Tensile means pulling load, compressive means pushing load. Similarly here, see, under tension, hence this is the tensile load. This surface will be experiencing tensile load, and here under compression, hence it will be experiencing compression, right? Now, so if you check, upper surface is what experiencing compressive load, that's the reason it is under compression, and bottom surface experiencing tensile load, hence it is under tension. But one surface will be there in between top and bottom, one surface or one layer will be there which will not be experiencing either tensile or nor a compressive load. Okay, that's very simple idea. Upper side is what under compression, bottom side is what under tension. So means in between somewhere the layer or somewhere the axis will be there or layer will be there where there is no load at all, that will be free of the loads, free of the tensile load, free of the compressive load. Yeah, there is no moment, there is no loads, nothing is there. That layer called a neutral layer. Hmm. That layer is what called neutral layer. See here, that layer is what called neutral layer, or it is also called neutral axis. Okay, always remember. So whatever the NA I am giving, this is the neutral axis, and this by experiment also it is proved this neutral axis is what not going to change. That length of neutral axis not going to change before load or after load. That neutral axis or that length of the neutral layer will be the same. Just previous what load you have applied or what moment you have applied, there is no effect on the neutral layer, there is no effect on the neutral axis, hence it is called a neutral axis or neutral layer. Okay, so always remember the layer of zero stress, the layer of zero stress due to bending is called neutral layer, and the trace of neutral layer in the cross section is called a neutral axis. So overall idea, this is 1 marks question also. At the same time, question will be like, okay, what is the load or what is the moment at neutral axis or neutral layers? You have to say there is no stress, there is no moment on neutral layer or on neutral axis. That's simple idea. Okay, this is the one thing. This is the physical appearance. Both are same only one is the sagging moment, other is what hogging moment. Rest the concept will be same. Okay, that is the one thing. Now coming to the derivation of it. Okay, I have to write few assumptions for this particular beam, like what type of beam you have to choose for the, I mean, what derivation you are going to uh, perform here, what formula you are going to achieve here, that formula when will be applicable, and what type of beam that formula will be applicable. For that we have to write the assumption first. So this two, 3 points we'll have for the, that is also called assumptions of simple bending stress. Okay, assumption of or assumptions for theory of simple bending. Okay, so assumptions I have to write assumptions. Assumptions for what? Assumption for simple bending theory. Okay, simple bending theory. Now what are the assumptions? Point one, check. The material is homogeneous and isotropic. This is very special. The material are homogeneous and isotropic. What is the mean of homogeneous? If the same type of material has been used uh, for the structure for the body, then that body will be called as, our structural component will be called as a homogeneous. Okay, if same type of material has been used. And isotropic means in all direction that property must be same for that structural member. If it is isotropic, then all in all direction you fix a point, and from the point in all direction that property will be same, then it will be called as isotropic. So two words are very important: homogeneous and isotropic. Homogeneous means same type of material has been used for the structural member, and second isotropic means if the property of the material is what same in all direction, that is called isotropic. So that is one thing. Second thing, this is the first assumption. Second assumption, the modulus of elasticity, the modulus of elasticity is the same in tension, is the same in tension and in compression. Okay, this is the second. Third, very important, stresses are within the elastic limit. Stresses are within the elastic limit, right? Fourth, plane section plane section okay, plane section remains plane even after deformation. After, meaning is, if you apply load on the plane, then it will be deformed, and once you remove the load, then it will regain its shape. Means it is remains plane even after deformation. There is no bulging at all. Okay, there is no bulging at all. The beam is initially straight and every layer of it's free to expand or contract. That is also one assumption. Okay, that is also one assumption. The beam is initially straight, and every layer of it is free to expand or contract, right? Correct. So these are the assumptions. Now we'll go for the derivation of bending equation. Okay, meanwhile I will give the definition of the neutral axis also, so you will always aware with this. Neutral layer, what is the neutral layer? See, neutral layer is nothing but the layer of zero stress. You need to remember the layer of zero stress due to bending is called neutral layer. Okay, what is the neutral axis? So neutral axis, okay, the trace of neutral layer in the cross section in the cross section is called is called neutral axis. Okay, this very small two liner definition we have, you need to remember always. Now we'll go for the derivation. Okay, now we are going to derive the bending equation. All right, so bending stress equation. Here we have to, better you say bending stress, better to say bending equation only. Okay, because here we'll derive both, we'll derive both, we'll derive bending stress as well as bending moment. Okay, bending stress and bending moment. Now what we have to do, simple, we have to take the diagram. Here we are going to first develop the relationship between bending stress and radius of curvature, and then we'll get the relationship between bending moment and radius of curvature, and once radius of curvature in both cases will be same, hence we'll equate, then we'll get the relation between bending moment and bending stress. Simple thing we are going to do. Okay, two steps we have. We are going to calculate bending stress. We are going to develop the relation between bending stress and it's a radius of curvature. I'll explain you what is the radius of curvature. Radius of curvature for the same beam, and similarly here also we'll have to develop the relation between bending moment and radius of curvature for the same beam, for the same beam. And you know very well, for the same beam, radius of, for the same structural member, if radius of curvature for both is same, obviously it will be same, then your bending moment and bending stress equation you can develop in that way. Simple idea. Okay, simple idea. So it should be very focused, like what we are going to do here. So we are going to develop relation between bending stress and radius of curvature, right? So check, we have to write relation between bending stress and radius of curvature. Check, for that we have to take a structural member. That structural member is nothing but, see, this is the structural member we have taken here. That part we have cut, this portion we have cut, it was very long structural member, but one small part we have cut and we have zoomed here. So we'll definitely get the different part of it. We can say inside this we have taken this one and this one. This is nothing but A, B, this is what C and D. In between, one is elemental thickness we have to take. This is the one elemental thickness. This is the one elemental thickness we have taken, and here the width of this elemental thickness is nothing but Y. Okay, you should be very aware about it. Now focus, each and every steps are very important, and this elemental thickness, whatever the elements you have taken from this structural member, that is nothing but EF G H. Now for this structural member we have to perform the calculation. Once we'll get for this, for whole structural member we can get. Now, very simple idea, simple calculation we know. If anything you are going to calculate for big structural member, so first we'll take one is small elements, and for that we have to perform calculation, and we can if once we got for a small element, then we can integrate and we can get for the full structural member, right? So that's the idea only. Now if you apply the moment, if you are apply the sagging moment for this structural member, so what will be the shape of this structural member? The shape will be something like this. See, I have to draw something like this. The structural member you will have something like this. Okay. Again, we are talking here for this particular section what we have taken ABCD. So this structural member will be something like this because we have applied the sagging moment here. Sagging moment, I have shown you when you apply the sagging moment, see this will be the physical appearance of the beam. Here we have applied the sagging moment, so this structure will be something like this. Okay, so just now here we have applied moment, so we can take we can take the section because all the lengths have been changed, so you can say this is nothing but a dash b dash. Okay, and obviously this is nothing but c dash d dash, and these elements what you have taken, these elements obviously it's also dimension will be changed. So see here, this is the elements. Remember, I'm not talking about any neutral axis here yet. Okay, I'm just talking about the elements. So this element also shape and size will change. Why I'm saying, because just now I have explained on element on neutral layer there is no effect of the load, so definitely this is not neutral layer or something. This is the one element we have taken, and this is nothing but g dash and h dash. So if you see here, so we have considered an element, it was AB length, okay, and just now you have seen that was the top. Okay, now if you see, the bottom layer is nothing but CD layer. Okay, now if you check GH layer, uh, we have taken this GH layer for the elements, taken Y distance. We have taken Y distance from the EF layer. So this EF, I told you, this is the one element we have taken. Now coming to this EF, now if you consider this is this is the nothing but the neutral layer. So from neutral layer EF, the distance is what, Y for the GH layer. Okay, from the neutral layer EF, we have taken Y distance for the GH layer. GH is the one layer we have taken. Okay, EF we are considering, if let EF be the neutral layer. Okay, I told you this one small elements we have taken, and I'm considering that small element, suppose EF is passing through the neutral layer, then you can consider EF as a neutral layer now, and from the neutral layer GH uh, layer is what, at Y distance. Okay, let me write here. So we can say, because we have taken one small uh, EF GH, this is the small elements we have taken. Okay, EF layer passing through neutral layer. Okay, and GH layer is Y distance apart from EF layer. EF layer, and what is the EF layer? Because it's passing through the neutral layer, so EF also considered as a neutral layer. Okay, it is clearly mentioned, so there should not be any confusion. 2 points I have taken, right? Now if you see this curvature we are getting, and with respect to one point we can take point O, we can take here, this is the point O, with respect to point O, this curvature we are getting here. Okay, and definitely for this curvature we can have end points, that is C dash D dash. Okay, and A dash B dash. So we can say from the neutral layer. What is the neutral layer now? Your E and F is the neutral layer. Okay, E and F are neutral layer. So that radius from the point O, about O where we are getting curvature, about O where we are getting curvature. So distance, radial distance from O to neutral layer is nothing but capital R. Okay, so I can take this point somewhere around here. See, I can take this point somewhere here, or I just want to reduce the diagram because of the space and all. So I can say my all point is what shifting, just little bit it is shifting inside, so the problem will be sorted. Okay, I can tell you this is the outer portion here, just like this one, and here this. Now I can take that 2 points along this. This now this is fine because of the space only. I am just reducing the size, so it will be more clear, no, for you. Check. I can give the naming. I can say this is A dash, this is B dash, this is C dash, this is what D dash. Obviously here this is nothing but E dash, this is nothing but F dash, this is nothing but GH, this is nothing but H, G dash, H dash. So my point is, if you are taking, now this is the point O, so because we are getting the curvature, so we have to measure the curvature about point O, with what angle it is curved, that we have to measure. Now we can take the radial distance from O to neutral layer. Where is the neutral? This is the neutral layer, something like this. And this curvature you may have, I think I have to draw another diagram because this one is because of the space only I'm facing problem. That's the reason. So the same diagram will have here. Only this one I'm just going to change. This is now curvature here. See now, yes, here I can able to explain each and every parts clearly. Right. This is the surface we cut somewhere. We cut from somewhere, and then we can take the point O, about which we are taking the we are measuring the curvature of this section, something like this. This is perfect now. Check. Right, this is the perfect now. We can say this is nothing but A dash C. Now this is the whole diagram, the same thing. A dash B dash, this is A dash B dash, bottom side C dash D dash, C dash D dash. Okay, I told you the small elements we had taken, EF and GH, where EF is what passing through the neutral layer. So this is nothing but E dash F dash. Okay, so E dash F dash, this is the neutral layer now, and here we have another layer called GH, G dash H dash, G dash H dash. And you know very well that distance, vertical distance between the neutral layer and GH layer, it was Y. Here I had shown you this diagram. If you see here, I had shown you here this one. This length is nothing but Y length. Vertical. I'm saying, okay, vertical distance. So now coming to check, this O is the point about which we are measuring the curvature, because now it is curved. So once we are going to measure the curved from one fixed point, then it becomes a curvature we are talking with respect to point O. So this angle also we can show. See, this curvature is now by the angle, if you show, it is nothing but phi. And obviously we have to measure one distance which is nothing but radius of curvature, and always remember radius of curvature will be measured from the points from where you are measuring the curvature to neutral layer. You consider this EF layer is what passing through the neutral layer, hence it is neutral, it is passing through the neutral axis, hence this layer will be the neutral layer, and this curvature will be defined by the radius of curvature. Okay, it will be defined by the radius of curvature. Basically, r, what is the r is nothing but radius of curvature, radius of curvature. Okay, and what is the phi? Phi is also, you should know, phi is nothing but the angle subtended, angle subtended, angle subtended by c dash, by c dash, c dash is here, by c dash, c dash a dash, means this line c dash a dash, this line basically, and d dash b dash, and d dash b dash, simple, at the center of radius of curvature, at the center of radius of curvature. Where is the center of radius of curvature? It's a point O. This point O is nothing but center of radius of curvature. Okay, now we have to start the derivation. It's very simple. You have to perform, because you consider that surface E dash F dash, which is passing through the neutral layer, hence obviously on neutral layer there is no extension in length, or there is no reduction in length. So because it's a neutral layer, so there is no load acting and all. So for that reason, E dash F dash will nothing but is EF. What is the EF? Just previous, before the load acting, EF was the length. But once you apply the, this called a sagging moment, this sagging moment, once you applied here, so because of that this shape will be changed, and once this shape will be changed, so definitely all the dimensions will be changed. But you consider that E dash F dash is what passing through the neutral axis. We can write here, we passing through the neutral axis, hence this E dash F dash is equal to EF, which is nothing but neutral layer, right? So because E dash F dash is what passing from through the neutral axis, and obviously you can call it now this E dash F itself a neutral layer, because passing through the neutral axis, it's a neutral layer, it's a neutral axis, anything you can call, then definitely that the length will be same. So but in GH we can get the strain, because GH is not passing through the neutral axis, so obviously GH length will be changed, right? So now we have to find what is the change in length, what is the change in length in GH. So we can write here change in length of GH. What is the change in length? That is delta L, obviously, and it is nothing but final length minus initial length. What is the final length? If you check after sagging moment, it becomes G dash H dash. What was the initial length? It was GH. Okay, GH. Now if I say what is the strain? Strain in GH, then it's nothing but final length minus initial length divided by initial length, that is GH. Means change in length by original length, no? That is nothing but strain. Here you know very well. Initially, what was the GH? See, initially, what was the GH? If you see, initially, GH was nothing but equal to EF. See, nicely. What was the GH? GH is nothing but EF before the moments. So before moment, GH is nothing but EF initial. Huh? But once after applying the sagging moment here, once apply the sagging moment here, so definitely that dimension will be changed. This is the sagging moment you have applied here, so curvature will comes into picture, right? So definitely initial, you can write initially GH is nothing but EF. Okay, so you can write strain and strain in GH layer. So definitely instead of GH you can place EF, and once you calculate EF, check how to get that value of EF from the diagram, because EF is now fixed. What is the EF? EF is nothing but neutral layer. Yes or no? So neutral layer is what now fixed, even though after the curvature also EF is what E dash F dash, which is fixed only. So now we can get the value of it. What is the value? How we'll get it? I'll show you. So you can say we can consider tan phi. Tan phi is nothing but E dash F dash divided by R. Okay, tan phi is nothing but E dash F dash by R. That is true only, right? It's a curvature, but we can consider a straight line, so we can apply the trigonometric relation. So it will be tan phi is equal to E dash F dash by R. Huh? Perpendicular by base both side, it is radius of curvature, which is constant. R will be same for both side. So obviously we can say tan phi is equal to E dash F dash divided by R. E dash F dash is also EF by R. EF also is nothing but GH by R, right? So clearly you got here tan phi, which is nothing but tan phi is nothing but GH by R. What is GH then? It's a R tan phi. We can write for very small angle. Can we say for very small angle tan phi approximate to phi? Yes, that is true. So basically GH is nothing but R into phi. Okay, that is true. This is what GH. We got GH here, right? But we have also GH dash. See, this is what? This is, if check the formula, G dash H dash. Na? So this is nothing but G dash H dash. We got GH value, but G dash H dash, we have to find G dash H dash. GH we got. Just now we got GH. See, GH is R5. But what about G dash H dash? Where is G dash H dash? See here in the diagram. G dash H dash. How you will get it? Where is G dash H dash? This is the G dash H dash. See, for E dash F dash, which is nothing but GH. Just now I had written E dash F dash is nothing but GH initial condition. But G dash H dash is not E dash F dash. Okay, just listen my point, you will understand. I am saying E dash F dash. E dash F dash is nothing but EF, because it's a neutral layer, so it will be same. And EF is nothing but GH. From the previous diagram, initially when there was no sagging moment, that time EF is equal to GH. So now for that reason, by this way, you have applied the concept and you got the GH value. But what is the G dash H dash? Because we also have to calculate. So G dash H dash also very easy. The same thing will be there, but only Y distance will be added. Where it will be added? In R. R plus Y dash, R plus Y, if you say, then it becomes G dash H dash, because see, this is what Y. Because this Y, or here we can take this Y. I know this is the vertical and this is the inclined, but I told you curvature is very small. So this Y and this Y you can equate. So now if you write G dash H dash, so definitely it will be R plus Y and phi angle will come. So now from the same we can write similarly. We can say similarly G dash H dash will be R plus Y into phi. Rest everything will be same. Right. So now your job is done. We are able to find the strain in GH. Okay, because strain in GH nothing but G dash H dash minus GH by GH. So G dash H dash and GH both we have. Now we can write the strain, because that is important. Strain in GH, it's nothing but G dash H dash minus GH divided by H. A little bit my G is what changing continuously. So try to understand it. Okay. So what is the strain in GH? G dash H dash, it's nothing but R plus Y phi minus GH, R into phi divided by R. This is what strain in GH. Okay. Now what is this value? Check. R phi plus Y phi R phi divided by R phi. Check this value. You have to cut this and this is what cancel out. Phi is cancel out. It's a Y by R. This is nothing but strain. This is very important here. This is very, very important. The strain in GH you have calculated. It's Y by R. So what is the Y? Y is the distance from the neutral axis to GH layer. It is already clearly mentioned. So once you got the strain, then stress will be very easy for you. Because if you see here, for the GH, where is the GH? It's a bottom layer. So in bottom layer, see, this layer is what under tension, can be say? Yes, it is under tension, because length you have seen strain is positive. So GH is what under tension, because this strain what you got, it's a positive. It's a positive, hence under tension. Hence under tension. Whatever the Y by R you got, it's a positive only. So strain is positive, it means it's under tension. If strain is negative, means it's under compression, right? Once you know the strain, can we write the stress for GH, or stress in GH? We can say it's nothing but sigma. Stress in GH is what? Sigma, as per Hooke's law. As per Hooke's law, we know that stress is directly proportional to strain, or stress is equal to Young modulus E into strain, right? Onward here you can say whatever the stress we got, sigma by E is equal to epsilon, that is strain. And what is the strain you got? See, just now you got strain in GH, Y by R. That means strain in GH. I will write each and every steps, I will write, so easily you can strain in GH. So sigma by E, just now you have derived strain in GH. It is nothing but, let me check, Y by R. Y by R. This is the first part you have done. This is the first part you have done. You have developed the relationship between stress and, it's a relationship between stress and radius of curvature. See, everything is what known. Sigma is nothing but stress in basically GH member we are calculating. So obviously in GH, R is radius of curvature for the section, and obviously Y is the vertical length from the neutral axis to GH layer, uh, perpendicular distance from neutral axis to GH. E is nothing but Young modulus. Young modulus. So we should aware with this. It's very easy. Okay, it's very easy. Now once we got this first relation, we also can develop the second part, which is nothing but the relationship between the stress and relationship between the moment and radius of curvature. So this will be equated in both, then we'll get the answer. Hardly it will take 10 minutes, so we have to perform now only. This is the first result we got. Again we have to write relationship relationship between bending moment and radius of curvature. Okay. What is the bending moment? It's nothing but m, that is sagging moment basically. What is radius of curvature? It's r. So we are going to develop the relation between these two, right? It's very easy, I told you. What we'll do here, see now, because we know the structural member we have here, this is the structural member, this is the structural member, and obviously we have seen the neutral axis also. This is the neutral axis now. Okay, this is the neutral axis now. We have taken, we can say this is the section and this is the neutral axis now. This is the neutral axis. Okay, from the neutral axis to one layer, that was GH. This length was Y. Okay, this length was, vertical length was Y, and neutral axis, as you know, it was EF. And we said EF GH was one elements where EF was passing through the neutral axis, that we know. So what we'll do, we'll consider one elements. Okay, we'll consider one elements which is at Y distance, which is at GH is now layer, and here we are taking one elements, and this element length is area is nothing but, we can say it's a elemental area. Elemental area is nothing but dA. Okay, that's the idea only, based on, because for moment you know very well, I have told you how to calculate moment of inertia, then moment also you can get in that way. So for that we should have a area, so we have calculated on it. Okay, now as you know, on GH layer, once we took area, then we can calculate what is the force on it. So stress already on GH we have calculated. Okay, what was the stress? uh, Stress on GH element. Okay, now element we have considered where the area we have taken ds. So on GH we have calculated stress. What was that? If you see back, go back and check what is the uh, stress we have calculated on GH. That was sigma we have calculated. So what is the sigma? Sigma is nothing but y by r into E. right? So sigma is equal to y by r into E. This is the stress on GH, right? Or we can say constant, we can take out E by R into Y, meaning is same. Now if I say stress we have, can we calculate force on the elements? We have taken elements on GH that and with elemental area dA, so we can calculate force on this element, which is on GH surface. So yes, we can calculate what is the force. Listen carefully, each and every steps will be very clear. What is the force? So the force is nothing but stress into area, right? Stress into area is nothing but force. So we can say ER y into ds dA. This is nothing but force. This is nothing but force. Now on the same, can we calculate moment about y-axis? So for this particular elements, we can write here again, next line, we can write moment of resistance. Obviously, moment of resistance, because already you have applied the sagging moment. So to resist that sagging moment, we can write moment of resistance of this element force about, we are talking about neutral axis, because from the neutral axis we know this is the GH. Just listen carefully. And this is what the EF, which is also nothing but neutral axis, E dash F, or simple EF also you can say. Or so EF is also neutral axis, that already I have told you. This GH length is given Y. Okay, that is the length is given Y. Already I have explained you. And on GH we have taken area, which is nothing but dA. That is the element. This is the element we have taken on GH. And elemental area is nothing but dA. So for this element, we want to write the moment. So what is the force acting on this element? It's nothing but this value. This is the force. What will be the moment about neutral axis? So force into perpendicular distance. What is the perpendicular distance? Y. So it's nothing but force into distance, perpendicular distance, it's Y. This will be the moment of resistance, and it is denoted by M. And this moment of resistance will be the bending moment. Yes or no? Equilibrium condition, I am saying. Equilibrium condition will be the moment of resistance will be the bending moment. Whatever load I am applying to the surface, the same force will be applied by the surface to me also, right? So bending moment is the moment what we are applying to the surface of the beam, but the beam also will resist that moment, which is called moment of resistance. So that must be same. So no need to introduce another moment like M dash or something. You just think it will be same in equilibrium condition. Okay. So M is nothing but force into Y. What is the force? It's a E by R into Y dA into this Y. Okay. Now you got here. Now you got here M is equal to E by R, you can take outside. Okay, E by R you can take outside. It's nothing but Y square dA. This is for the small elements I have taken. I told you that elements we had considered elemental area dA, but once you complete for all full surface, so it by R integration of Y square into dA. What is this Y square into dA? If you remember, it is nothing but moment of inertia. This is nothing but moment of inertia. I need to write MOI, moment of inertia, Y square dA. So M is nothing but E by R into I, that is the moment of inertia, which is also called second moment of area about centroidal axis. I hope you remember that. So ultimately we got M by I is equal to E by R. Okay. M by I is equal to E by R. If you check, this is the relationship between the bending moment M, and R is the radius of curvature. So this is the second equation you got. That is the relation between M and R. R is nothing but radius of curvature. Radius of curvature, and M is nothing but bending moment. This is also moment of resistance, but at equilibrium it must be same. No? At equilibrium it must be same. So automatically, if you check the previous equation, what you got there? You got sigma by E is equal to Y by R. So first you got sigma by Y, sigma by Y is equal to E by R. From here, what you will get? Sigma by Y. You can write here sigma by Y is equal to E by R. Right? You can write here sigma by Y is equal to E by R. This is the first equation you got. Second, what you got? M by I. Check just now. M by I is equal to E by R. Yes or no? M by I is equal to E by R. This is the second equation. If equation 1 and 2, because E by R is what common for both, so we can write R, the full relation we can write. It's nothing but sigma by Y is equal to M by I is equal to E by R. Check if I am not wrong. This is the master equation for the bending stress. This is the master equation for the bending stress here. All right, this is very powerful, very important equation, right? So now again I will write sigma by Y is equal to M by I is equal to E by R, or you can write M by I sigma by Y E by R. Okay, anything you can write, it's your choice. uh, which will which is first, it's not important. Important is all the components E by R. Now each and every term is very important, and you need to remember that. Already I have explained you M, I have explained I also. Then also you need to remember what is the sigma you have to write. Also you need to remember Y. Also you need to remember E. Also you need to remember R. Each and everything I will write one time. So next you just remember what is M, bending moment at the section. At the section. What is I? I is moment of inertia about centroidal axis. Moment of inertia about centroidal axis. What is sigma? Sigma is nothing but obviously bending stress. What is Y? There should not be any doubt. It's a distance of 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 the surface from neutral axis. What is the surface? It's a GH. Distance of GH from neutral axis. Instead of GH, now you can say it's a element. You can take it's a fiber. You can take it section, any name you can give, because GH is arbitrary name I had taken, but you can consider it's your choice what you want to give. E is nothing but modulus of elasticity. R is nothing but radius of curvature of bent section. Point about center of curvature, that was point O. So radius of curvature, I must write only radius of curvature. Clear only. because for the curved section only we'll have a radius of curvature. If it is a plane surface, then what is the radius of curvature? It's infinite. So all done there, right?